So far in this course, we've really been focusing on general function properties, domain, range, intervals of increase, intervals of decrease, how to build a model, not for necessarily a specific type of function. We're going to change our focus now and start looking at specific function types one at a time. And in this chapter, the function type we're looking at is called a polynomial function. We'll spend time digging into the details of how to come up with the x-intercepts of these types of functions, how to know what the general behavior is at what's called the end behavior of the graphs, and then we'll look at word problems that are tied to this type of function. And that you'll see that for the rest of this course. Now we'll look at specific types of functions. So polynomials first, then we'll look at rational functions, then we'll look at exponential and logarithmic functions, and then we'll switch gears again and look at what are called systems of equations and inequalities. But for a while now, we'll have a little bit clearer focus, not talking about broad general properties of functions, but about very specific types of functions. So here we go. We'll start with polynomial functions. Our objectives in this particular video are to identify what a polynomial function looks like, how can we recognize one if given the formula, and then to graph polynomial functions using two different techniques. First, just using transformations of what are called power functions, and then if we can't see it as the transformation of a power function, looking for the real zeros and talking about the multiplicities of zeros, which is something we'll define, and then using the zeros and the multiplicities to sketch a graph. So, definition first. A polynomial function, that's what we're trying to define here, is a function of this form, and this looks complicated, but we've got a coefficient times x to the n, another coefficient times x to the n minus 1, and so on. This pattern, coefficient times x squared plus coefficient times x plus a coefficient. So what we see here is just a sum of terms where each term is a constant times x to some non-negative integer power. So we don't have any x to the negative 1 or x to the negative 2. We don't see any square roots, right? So the subscript on the coefficient goes along with, matches the exponent on the variable. So a sub n, x to the n, a sub n minus 1, x to the n minus 1, and so on. We would have a3 x to the third plus a2x squared plus a1x. And then keep in mind a sub 0, we could think of this as x to the 0, because anything to the 0 power is 1. So we don't write x to the 0 there, but it does fit that same pattern. The domain of a polynomial function is always all real numbers. There's never a reason to have any restriction because we don't have any variables in the denominator and we don't have any square roots. So we can take any real number and raise it to a power and multiply it by a constant. So x doesn't matter what x is, we can find the output. So that's important. Any polynomial function has all real numbers for its domain. So the first example here is just asking us to look at these functions and decide, are they polynomials or not? In this definition above, there's one other term we should define, and that is the degree of the polynomial is the exponent on the term with the highest exponent. So in this example, if a sub n is not equal to 0, then the degree would be n. If a sub n is actually 0 and there's not an x to the n term, then we would look at the first term that's non-zero. So whatever the highest exponent is, that's the degree of the polynomial. That's another definition that's important. So here we have two goals. First, figure out whether we even have a polynomial function, and if we do, figure out the degree. It's standard to write polynomials in what's called descending order. So here I notice, well, x to the fifth is the highest exponent I have, so I would rewrite this in the order negative 8 x to the fifth plus 3x squared. So in this case, the degree is 5 because the highest exponent is 5. This is a polynomial because the only types of terms I see are x to some non-negative integer power times a constant. So this is a polynomial, and it's degree 5. Because 5 is the highest exponent. The next one isn't as obviously a polynomial, but if we do some rewriting, we can see that it is. If I expand the numerator, I have x cubed minus 4x. And I have division by 7 of the whole thing, but I can always rewrite that as 1/7 times x cubed minus 4/7 times x. And now I see that my terms are all constant times x to some non-negative integer power. So that is also a polynomial, and its degree is 3. The highest exponent is 3. The next one, we have division by x minus 5. So the difference between these two, there's division in both, but in the first one we were able to rewrite that division as multiplication by just a coefficient that happened to have a constant denominator. This one we can't do that. There's no way to rewrite this so that we have a polynomial left. So this, we have division by a variable. So this is not a polynomial. The numerator by itself is a polynomial. The denominator by itself is a polynomial. But one polynomial divided by another polynomial is not a polynomial. That's what's called a rational function, and that's what we'll be looking at in a few videos down the road. The next one looks tricky because it involves the square root, but the square root is on the 3, so this is not a problem. This is still just a constant times x to a non-negative integer power minus another constant times x to a non-negative integer power plus a constant. So the terms are all the form we want for polynomials. So this is a polynomial, and it's degree 7 because x to the 7th is the highest degree term. If you want to just make a note, a7, the coefficient on x to the 7th, is square root of 3, and a1, the coefficient on x to the 1, is negative pi, and a0 is 2. You don't need to write that by any means, but I just wanted to tie it back to the notation from the definition since I hadn't done that yet. All right. Then, example E here, again, we've got something that's written in factored form, but anytime we have something in factored form, if the factors are individually polynomials, then when we expand it, we will have a polynomial. So the product of polynomials is itself going to be a polynomial. We can expand this and see what we get. We'd have x squared plus 2x when I multiply the first two together, and then I'd take that answer times x cubed minus 2x, and I'll get x to the 5th. Remember to add exponents when you're multiplying if the bases are the same. Plus 2x to the 4th minus 2x cubed minus 4x squared. So it is a polynomial, and its degree is 5. Because x to the 5th is the term with the highest exponent. Notice that if we look at the factors, the first factor is degree 1, the second factor is degree 1, the third factor is degree 3. If we add those up, we have 1 plus 1 plus 3. That gives us the degree overall. So without expanding it, we could say, okay, I'm going to have an x times an x times an x cubed. That's going to be an x to the 5th. That's the highest degree I'm going to have. Excuse me. So if the question it doesn't ask us for the expanded form, if it's only asking us for the degree of the polynomial, we can figure the degree out without actually getting the entire expanded form. Alright, then the last example here, we've got h of x is 5x cubed times the quantity square root of x plus 5 cubed. We're going to have a problem here because of this square root of x. There is not, the square root of x or square root of a variable is not allowed in polynomials. So polynomials don't include the square root of x. So this is not a polynomial. Even if we were to expand this and cube this out, there's still going to be a square root of x involved. So this just won't be a polynomial. So we only had two that weren't. C and F were not polynomials. One other term that we should talk about is called the leading coefficient. The leading coefficient is the coefficient on the highest degree term. So in the first example, the leading coefficient is -8. Because that's the coefficient on x to the 5th. In example B, the leading coefficient would be 1/7. In example D, the leading coefficient is square root of 3. And example E, the leading coefficient is 1. On x to the 5th. Knowing the sign of the leading coefficient is going to help us know a little bit about the shape of the graph. That's why it's important to define that term, and that's why we sometimes look at that coefficient and ignore the others when we're wanting to know what the graph might look like. Okay, so the next definition we need is called a power function of degree n. And a power function of degree n, it says, is a monomial, so a single term. Polynomials can have multiple terms, but a monomial is a single term, a function of the form constant times x to the n, where n is a positive integer and a is not 0. Any real number that's not 0. So, for example, f of x equals 2x cubed, or f of x equals -4x to the 6th. Those are called power functions. And if n is even, the graph will look like x squared. or it will look like negative x squared. But I guess if it's just x to the n, it'll look like x squared. If we allow a negative coefficient, then it could be upside down. But if this is just x to the n, if n is even, whether it's x squared, x to the fourth, x to the sixth, the graph is going to have this shape. So there will be y-axis symmetry. The domain will be all reals. And the range will be 0 upward. Key points that will be on any of those graphs would be 0, 0, 1, 1, and negative 1, positive 1. If I have an even exponent, negative 1 squared, or negative 1 to the fourth, or negative 1 to the sixth, those are all going to give me positive 1. So the general shape is going to be like a parabola. The higher the exponent, the steeper the graph is going to be when we're outside of 1 or negative 1, and the flatter the graph will look between negative 1 and 1. For n odd, the graph is going to look like x cubed, roughly. So we're going to have origin symmetry. We'll have domain and range, both all reals. That looks like a square bracket on my infinity. I don't want that. The key points we would have on all of the graphs would be 0, 0, 1, 1, and this time instead of negative 1, positive 1, we'd have negative 1, negative 1, because negative 1 to the third is the same as negative 1 to the fifth, is the same as negative 1 to the seventh, and they're all negative 1. And then the general shape is up there. So if I'm going to sketch the graph of this function using transformations, I want to figure out which function to start with, and I see this exponent 3, so I'd want to start with y equals x cubed, and then track what transformations I need. And it's probably easiest to rewrite this function as putting the plus 3 on the end. So I have a multiplication by negative a half. I have added 2 to my input before I cubed it, and then I'm adding 3. So this multiplication by negative 1/2 will be a reflect over the x-axis, and also it will be a vertical change because it's outside, so vertical compression by a factor of a half. X plus 2 is going to be a left 2 shift. Remember, the cube is the thing that's giving me my shape, and then the plus 3 on the outside is going to be an up 3 shift. So I want to start with some key points on x cubed, and we had 0, 0, 1, 1, negative 1, negative 1, and let's find one more that would distinguish it from x to the fifth, for example. How about if we use 2, we would have 8. Let's do the reflection over the x-axis. That's going to change the y-coordinates. So now we'll have 0, 0, 1, negative 1, negative 1, 1, and 2, negative 8. Then we want to do our compression vertically by a factor of a half. So 0, 0, 1, 1/2, -1, oh, sorry, that should be -1/2, -1, +1/2, and 2, -4. Then we want to do left 2 and up 3. I'm going to do these together. Left 2 is going to change the x. Up 3 will change the y. So left 2, up 3, that's going to be +2.5. Left 2, we'll take that to -3. Up 3, 3.5. Left 2, that's going to go to 0. Up 3 is -1. So my points should be -2, 3, -1, 2.5, -3, 3.5, and 0, -1. I could also track what's going to happen. I would have had -2, -8 on my original graph also. If I reflect that, I have -2, 8. Compress it vertically, I have -2, 4. Go left 2 and up 3, that's going to be -4, 7. So let's include that point too. Now we can see how this graph is going to fit together. So there's our graph of 3 minus 1/2 times the quantity x plus 2 to the third. And again, we are using transformations of the graph y equals x cubed, doing the shifting last and the reflection and the vertical compression first. Alright, so graphs of polynomial functions always have the same look. They're what's called smooth curves, which means there are no breaks or corners. So you won't have something like that. You won't have any corners like that. And you won't have any disconnected pieces, so you would never have something like a piecewise function that does that. So these are not polynomial graphs. We can't have things like that. We don't have breaks and we don't have corners. Right? So polynomial graphs would have more this kind of shape. This looks like it's almost not a function because it's almost vertical, but let's do that again. So that kind of shape for polynomial graphs. Smooth edges and connected, continuous. One of the things we're going to be concerned with about a polynomial graph is what's called the end behavior of the graph. And the nice thing is that the only piece of information we need to know what the end behavior will be is the leading term. We need to know what's the sign of the leading coefficient and what's the degree of the highest degree term. And this isn't a proof by any means, but if we compare these two graphs, 2x cubed plus 4x minus 5, and 2x cubed, those two graphs on a very large window, and also on a smaller window, we can see that though they aren't the same graph, they have the same behavior in the long run. So grab your calculator and enter these two graphs. So 2x cubed plus 4x minus 5 and the other one just the highest degree term, so 2x cubed. And they're suggesting a couple windows here. The first is negative 10 to 10 for the x, and then negative 2000 to 2000 for the y. So negative 10 to 10 for the x, and negative 2000 to 2000 for y. And we'll make our y scale like 500 so that we can see the spacing. Okay, let's take a look. So there's one graph and the other. It's hard to tell them apart in that window, right? So they have the same long-term behavior. But if we change the window and look at what's going on just between x equals negative 3 and 3, so take a narrower view, and it says do negative 20 to 20 for the y's. In that window we can see they actually are quite different. So they're different close to 0, but the farther we get from 0, the more they look the same, right? You could look at another example. Let's do, I don't know, negative 3x to the 4th minus 5x squared plus 3x minus 7. And I just kind of made that up randomly at something degree 4 with a negative coefficient. And then I want to look at the graph that's the same leading term, so the same negative 3x to the 4th, but ignoring all the others. So just that leading term instead. And let's do the same thing. Let's look at a window from negative 10 to 10, say. And larger values even. Let's do negative 10,000 to 10,000 for the y's. Again, you can't really see much difference between the two graphs, so they have the same behavior in the long run. But if we narrow in like negative 3 to 3 again, if we do a zoom fit, we'll see, yeah, they're not really the same graph. They look like they were in that wider window, but in this little interval we can see they're different. All right, so the point of that activity was just to realize that the end behavior, the behavior for large x values, is all determined by the highest degree term. So if we have ax to the n as our highest, so if the highest degree term is ax to the n, let's say, we have 4 categories. We have ax to the n, where n is even and a is greater than 0. We have ax to the n, where n is even and a is less than 0. We have ax to the n, where n is odd and a is positive. And we have ax to the n, where n is odd and a is negative. So the sign of a and the even or odd property of the integer will determine what the end behavior looks like. For n even and a positive, the graph on the ends will look like y equals x squared. And the way we're going to write this is the function values go to infinity. They get higher and higher. The y values approach infinity, grow without bound as x goes to the left, as x goes to negative infinity, and the function values go to infinity as x goes to the right, as x grows without bound in the positive direction. So we want to say what happens to the function as x goes to the left, what happens to the function as x goes to the right. And we want to talk about that behavior in each of these cases. If n is even and a is negative, this graph just looks like an upside down parabola. So we don't know what's going on in the middle, but on the ends we know it's going to look like this. So this time we again want to say, instead of the function going to positive infinity, the function goes to negative infinity. It's unbounded in the negative direction as x goes to the left, or as x is unbounded in the negative direction, and the function values are also going down, 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 unbounded in the negative direction as we move to the right. So as x goes to infinity. Then we want to take a look at the odd integer exponent cases. So if we have like 2x to the third, then the ends of the graph will look like the ends of the x cubed graph. As we go left, the function values are going down. So we would say f of x goes to negative infinity. It's unbounded in the negative direction as x goes left, which means x goes to negative infinity. And f of x is going up in the positive direction, so to positive infinity, as we move right, as x goes to the right, to infinity. And then finally, if a is negative and n is odd, then we've got end behavior that looks like this. And in this case, we would say, as we go left, the function values appear to be going upward without bound. So f of x goes to positive infinity as x goes to negative infinity. And as we move right, the function values are dropping without bound. So f of x goes to negative infinity as x goes to the right, or as x goes to infinity. Right? So notice in each case, we're always looking at as x goes to the left and as x goes to the right. That's consistent, right? Always as x goes to negative infinity and as x goes to infinity. X is the independent variable, so we let x go left, we let x go right, and then what happens to the function? That's the thing that varies from one to the other. So we always let x do the same thing. Let x go to the left, unbounded, let x go to the right, unbounded, and then see what happens to the dependent variable. What happens to the outputs? Do they go up, or do they go down, or does one go up and one go down? What we're talking about here is called limits at infinity, and limits are something you're going to cover extensively when you get to calculus. But this is just kind of foreshadowing that idea, starting to use this notation with these arrows. So it takes a while to get used to it, but maybe just review this part of this video a few times. I think hopefully it will help. So, for example, let's just look at two of them. F of x, if I have 3x to the 6th minus 2x to the 4th plus 3x minus 7. The end behavior will be determined by 3x to the 6th, because that's the highest degree term. There's an even exponent and a positive lead coefficient. Even exponent means it's going to be like x squared or negative x squared. Positive lead coefficient means it's going to be like positive x squared. So the picture of the end behavior is like that. So we want to write it in symbols. So what's going on as x goes to negative infinity? Think of left. What's going on as x goes to infinity? Think of right. And we want to fill in, here's what f of x does. And in this case, f of x is positive, unbounded in both directions. So the function values are going to positive infinity, both as we move left unbounded and as we move right unbounded. One more. If I have f of x equals 5 plus 3x squared minus 4x to the 5th plus x cubed. The end behavior for this is all determined by this term, because that's the highest degree. So it's determined by negative 4x to the 5th. So that's got an odd exponent and a negative leading coefficient, which means it's going to look like upside down x cubed. So we'll be going like this on the ends. So as I go left, the function values are going up, unbounded in the positive direction. And as I go to the right, as x goes to infinity, the function values are unbounded in the negative direction, so they're going down. So the leading term is going to tell us about the end behavior, and then in order to get more information about what's going on in the middle of the graph, we're going to use what are called the zeros of the polynomials, which are tied to the x-intercepts. So these terms or these phrases are all going to be happening together. So what we want to do is draw arrows connecting them, that if one happens, they all happen. They're all interchangeable. So if we know that c is a zero of the polynomial, that we put in c, we get 0, that means that x equals c would be a root or a solution to the equation the polynomial equals 0. And it also means that x minus c is a factor of the polynomial. And it also means that c0 is an x-intercept of the graph of the polynomial. Right? Because c0, if that's an x-intercept, that means the y values there are 0. So all of these are tied together. So as soon as we know one, we know a bunch of other things. This is demonstrating that it's key to know the factored form of the polynomial so that we can use the factored form to find the x-intercepts. So for this specific polynomial, which happens to be degree 2, so it's one we're pretty comfortable with, if I want to find the zeros, I want the factored form, which would be x squared minus 2x minus 3 equals, what, x minus 3 times x plus 1. So that's my polynomial in factored form. So if x minus 3 is a factor, then 3, 0 would be an x-intercept, and if x plus 1 is a factor, then x equals negative 1, so negative 1, 0 would be an x-intercept. So the x-intercepts are 3, 0 and negative 1, 0. the zeros of p, we list them slightly differently. We don't list them as points, but x equals 3 and x equals -1. So 3 and -1 are the zeros of a polynomial. And x equals 3 and x equals -1 are called the roots of the equation x squared minus 2x minus 3 equals 0. The end behavior is like positive x squared, right? So we know the end behavior is going to be going up on both sides. And we can see pretty easily that the y-intercept is -3. We might as well have that accurately. So there's a sketch. And the end behavior, we can say, using those symbols, the function is going to infinity as x goes to the left, and the function is going to infinity as x goes to the right. So as we move left or as we move right, the function is going up without bound. So now we're going to look at a polynomial that's not a quadratic, so it's not a parabola graph, and use the end behavior and the zeros to sketch the graph. So again, the factored form is key. So we want to start with that. So p of x is -x to the 4th minus 6x cubed minus 9x squared. Always look for a greatest common factor first, which in this case would be, we could take out a -x squared. And we have x squared then plus 6x plus 9. If we factor out a -x squared, the signs will change across each term. And we can factor that second group again. We'd have -x squared times x plus 3 times x plus 3, which I could write as the group x plus 3 squared. All right, so now what we want to think about is, what's the end behavior? And we can say it will be like -x to the 4th. Because that's the highest degree term. So it'll be down on both sides, like that. And here we can see the x-intercepts are -x squared equals 0, or x plus 3 squared equals 0. In either case, we're just going to get one solution. We have x equals 0 for this, and we have x plus 3 equals positive or -0, which is just 0 there. So x equals -3. Notice this is not x equals 3 or -3. We can't take x equals 3. That would give us a 6 squared. So it's just x equals -3. So we just get these two possible x-intercepts. The zeros of p are x equals 0 and x equals -3. And one more thing we're going to start talking about is called the multiplicity of the zeros. So x equals 0 because that factor x squared has an exponent 2. We say the multiplicity of that 0 is 2. Similarly, since the x plus 3 factor has an exponent 2, we'd say that this has a multiplicity 2. So a definition, the multiplicity of a 0 is defined to be the exponent on the factor related to that 0. Right, so both of these factors had exponents 2, so those zeros are said to have multiplicity 2. So if we go back to the previous example, these are both multiplicity 1 because there was just one factor of each one. So we could say both multiplicity 1. And the behavior at the x-intercept depends on the multiplicity. Notice for these that were both multiplicity 1, the graph just went right through those x-intercepts. But you'll find that when the multiplicity is even, like it is here, the behavior is a little bit different. Let's see what's going on with these. Alright, so we want to pay attention to 0 and -3. And what we're going to do is, just this one time, we're going to use the table on our calculator to find what's going on with the x values close to 0 and close to -3. So let's put this function in here. We had negative x to the 4th minus 6x cubed minus 9x squared. So I don't want to look at the graph, but what I want to look at is a table. I'm going to do table set. I'm going to do ask for my independent variable so that I can just plug in the values I want. And I want there's a way to clear this table, and I don't remember what it is, and it doesn't really matter right now, so maybe delete. Yes, delete, delete. All right. So what I want to do is I want to put in x values that are close to 0 to see what's going on with the y values. So I'm going to do -0.1, -0.01, -0.001, and then the same thing on the other side, 0.001, 0.01, and -0.1, or sorry, 0.1 positive. Notice that these are all negative values. These that say -9, e, -4, that just means -9 times 10 to the -4. So it's a really small value, 0.009, but it's negative. And this would be 0.000009, but still negative. So notice that all of them are negative. So on either side of 0, we have negative y values. I'll make a copy of this. So the y is less than 0 on both sides of x equals 0. So x equals 0 is an x-intercept, but the graph doesn't cross the x-axis there. Let's go see about close to x equals -3. So if I do something a little to the left of -3, so -3.1, not 31, -3.1, that's -3.01, still negative. Let's go on the other side, -2.9, still negative, right? So on either side of, I'm going to get get rid of some of these because I want to show them on the table. So we said negative 3.1 and negative 2.9. On either side of negative 3, the function values are also negative. So y is less than 0 on both sides of x equals negative 3 also. So we know the end behavior is going down on both sides. We know that on either side of this x-intercept, the graph is negative. Same on this one. So what happens is that these zeros of multiplicity 2, the even multiplicity, instead of crossing the axis, the graph just kind of turns around there, just like it does on x squared. So x squared would have a factor that shows up twice, and the graph turns around at x squared. So here, where the related factors have an exponent 2, we see the graph turn around just like x squared does. So what we're going to see is that if we have an even multiplicity 0, the graph turns around or bounces off the axis at the related x-intercept. But if we have an odd multiplicity 0, then the graph crosses the x-axis. At the x-intercept. And that's what's coming up in the next table. So if the multiplicity is odd, so for example, x plus 2 cubed has the negative 2 has multiplicity 3, which is odd, then the graph crosses the x-axis at the x-intercept negative 2, 0. So I don't know what the rest of the graph would look like, but maybe the graph is going to cross like that. But if the multiplicity is even, as in the case of, say, x minus 1 to the 4th, the multiplicity is 4, and we would say 1 is the 0, has multiplicity 4, which is even, and the graph will turn around at the point 1, 0. So who knows what the rest of the graph looks like, but around that point the graph is going to look like this. It will come down and just touch the x-axis and then turn around. All right, so continuing with some examples of graphing polynomial functions, keeping in mind what we learned about the end behavior being determined by the highest degree term and its coefficient, and the behavior in the middle of the graph being much determined by the x-intercepts and the multiplicities of the zeros connected to those x-intercepts. Let's go through this example 6 here. So we want to know the degree and the sign of the leading coefficient so that we can figure out the end behavior. So these two pieces will help us know the end behavior. And the degree is easier to see if we have this in expanded form, but we mentioned earlier that if we have the factored form instead, what we can do is count the degree of each factor. So we have a degree 2 factor, and this factor here is degree 1, but there are 2 of them, so that would have another x squared. And then the last factor is degree 1. So when we multiply these together, we would have degree 5. You can imagine that I have this x squared, and then I'd have another x squared from this. That would be the highest degree term I have, and then there's an x in the last one. So just multiplying those together would give us an x to the 5th. So this is degree 5, and we can determine that without actually finding the expanded form. The leading coefficient is just going to be 1 in this case because we have a coefficient of 1 on all of these x's. So when I expand it, I would have just a single 1 x to the 5th term. So there's a positive lead coefficient, and it happens to be positive 1. So putting those things together, the graph on the end behavior is going to be like an odd exponent, or an odd degree power function with a positive coefficient on the front. So it would look like this. So on the ends, we'd say that the function is going to negative infinity as x goes to negative infinity. So as we move to the left, the function goes down, and the function is going up unbounded as we move to the right, so as x goes to infinity. Then what we want to do is use the zeros and their multiplicities to figure out what's going on in the middle of this graph. And the factored form is exactly what we need for that piece. So we want to know, where is the function 0? So we have the factored form, so we would set each factor to 0. So we've got x squared plus 3 equals 0, x minus 2 squared equals 0, and x minus 5 equals 0. X squared plus 3 equals 0 is the same as x squared equals negative 3. There are no real solutions to that. So this factor does not contribute to our x-intercepts. This would be x equals positive or negative I times the square root of 3. So only complex solutions. Here we'd have x minus 2 is positive or negative square root of 0, but that's just 0, so x minus 2 equals 0, which means x equals 2. So again, be careful, don't say that that's x equals positive or negative 2, it's just 2. The positive or negative would go on the 0, and those are the same thing. And then lastly, x equals 5 we would have. So remember, the zeros and their multiplicities tell us the x-intercepts, because this is where the function is 0. So there were no x-intercepts connected to this first factor. X equals 2 is an x-intercept of the graph, and this 0 is multiplicity 2 because of the exponent 2 on that factor. and x equals 5 is multiplicity 1. So at the x-intercept 2, 0, because that factor had an exponent 2, the graph is going to turn around because of multiplicity 2 on the related factor. But at the x-intercept 5, 0, the graph will cross the axis because of multiplicity 1. So any factor that has an even exponent, the related x-intercept is going to be a place where the graph turns around. Any factor with an odd exponent, the graph is going to cross the x-axis at that x-intercept. So that's enough information to get us a decent graph. We should also maybe just calculate the y-intercept, even though it wasn't asked so far. The y-intercept is putting x equals 0 in. So the polynomial evaluated at x equals 0 would be 0 plus 3 times 0 minus 2 squared times 0 minus 5. So we get 3 times negative 2 squared, which would be 4, times negative 5. So it looks like negative 60. So the y-intercept is 0, negative 60. So we've got x-intercepts at 2 and 5, a y-intercept at negative 60. We'll just put that down here. And we know the end behavior is like the x to the 5th graph with a positive lead coefficient. So like we had sketched up there. So we know the graph is coming this way and down on the other side, heading to negative infinity. So the graph is going to have to come through negative 60. It'll have to get to this x-intercept at 2, but there it's going to turn around, and then somehow it's got to get back up to the x-intercept of 5 and cross the graph there, and then it will continue up. So somewhere between 2 and 5 there has to be a low point, a relative minimum, so that the graph can come back up to that x-intercept. But at 2, 0, the graph is going to turn around. It's not going to cross the x-axis because of the multiplicity of the related factor. And at 5, 0, the graph is going to cross the x-axis because of the multiplicity of the x minus 5 having exponent 1. So the end behavior is as we expected. We've got this y-intercept labeled, and then we've got these x-intercepts with the behavior like we know we should have at those x-intercepts. That's good enough for a graph. We don't care about the rest of these y values. We don't know how low this point would go without grabbing a calculator, but this is a decent sketch of the graph, at least with the general shape and the correct x and y intercepts. Okay, so another example similar to that one. Our goal in the end is to sketch the graph, and we'll do that by taking a look at these pieces. Again, the degree and the sign of a leading coefficient will determine the end behavior, so we want to think about that separately, and then we'll look at the x-intercepts by looking at the factored form and the zeros and the multiplicities. So the degree here, again, what we want to think about is how many factors of x do we have? We have an x cubed, and then from this second group we'd have another x squared, and in the last one we have a factor of negative 2x. So it looks like we would have 1, 2, 3, 4, 5, 6 factors of x when we expand this. So the expanded form is going to have the highest degree term being degree 6. And that is going to come from 1/2 x cubed times x squared times negative 2x. So when we multiply all of the x's together. So that highest degree term is going to look like negative 1 times x to the 6th if we multiply the 1/2 and the negative 2 together. So we can see that the leading coefficient is actually going to be negative. So the fact that it's even degree with a negative leading coefficient means the end behavior is going to be like an upside down parabola. So that's the picture. We would say f of x is going to be unbounded in the negative direction as we move right. So as x goes to, left would be negative infinity. And also as we move right, the function will be going unbounded in the negative direction. So both ways, left and right, the function values are just dropping off. So again, we don't need the entire expanded form. We really just want to know what's that highest degree term going to look like. So we can multiply the 1/2 x cubed, an x squared, and a negative 2x together to figure out what that first term would be. And now the factored form is really what we want to use for the zeros. Again, so we'll set 0 equal to the function. All right, and so now we want to set each factor to 0. The first one, if I take the cube root and multiply everything, first multiply everything by 2 and then take the cube root, I'm just going to get x equals 0. The next one, I take the positive or negative square root of 0 again. That's just 0. So x plus 2, it's just going to be 0. So x is negative 2. So far, 2 x-intercepts, one at 0, 0, one at negative 2, 0. And then the last one appears to be at x equals 1/2. So those are the zeros. Let's write down also their multiplicities. This is multiplicity 3 because of the exponent 3 on the x factor. The next one is multiplicity 2 because of the 2 exponent on the x plus 2 factor. And then the last one is multiplicity 1 because there's just one factor of 1 minus 2x. So at the x-intercept 0, 0, the graph will cross the axis because that multiplicity is odd. And at the point negative 2, 0, because this is even multiplicity, the graph will turn around. So again, remember the multiplicity is just tied to that exponent. That's all we're looking at, not the value of the x-intercept. And then finally at the x-intercept 1/2, 0, because that had exponent 1, that related factor, we will have the graph crossing the x-axis again. Okay. Let's see, we also probably for the graph want the y-intercept. We saw that 0, 0 was an x-intercept, so we know that's also the y-intercept, but if you didn't catch that, you can evaluate p of 0, and we just have 1/2 times 0 cubed times 2 squared times 1 minus 0. That's just going to be 0. So the y-intercept is 0, 0 also. Okay, so putting this together and just getting a sketch of this graph with the correct end behavior and the correct x and y intercepts and the correct behavior around the x-intercepts, let's see what we can do. So the x-intercepts are 0, 0, negative 2, 0, and 1/2, 0. And the end behavior is down on both sides. So we're going to be coming up to this x-intercept, and we look at the multiplicity. It was 2. That's even. So we turn around there. Then we come up to the next x-intercept. At 0, 0, that was multiplicity 3. So we're going to come up to this, and then at this place, the graph is going to cross the x-axis, and if you want to be really careful about it, it would look almost like x cubed right there. So it's not going to go straight across, but it's kind of level out and then go up again. If you go straight across, I'm not going to worry about it too much as long as you cross the x-axis there, because that's an odd multiplicity 0. And then we need to get back down to 1/2 and cross the x-axis there. So there will be a relative high point, and that one would go straight across because this is multiplicity 1. So rather than leveling out and then going across, this would just kind of go straight across. And then we'll go down on the other side. So again, I'm not going to be concerned about the high and low points here unless you're given a calculator use, but you should be expected to be able to put a graph like this with this much detail together without a graphing calculator. So the correct end behavior, the correct x-intercepts, and the correct either crossing the x-axis or turning around at each x-intercept. Alright, so then the next example is just asking us to use a graphing calculator to analyze the polynomial. When it's something like this one, there's not a way we're going to be able to factor that. The numbers are just a mess. So some of these things we should be able to do without a calculator, so let's do those first. The end behavior is one of those. It's going to be like x cubed because that's the highest degree term. So on the ends of this graph we're expecting this, so the function is going to go to negative infinity, unbounded in the negative direction as we go left, as x goes to negative infinity. And the function is going to go up, so unbounded in the positive direction, going to infinity, as we move right, or as x goes to infinity. The x-intercept's not very easy to see without a graph, because we can't factor this easily. But the y-intercept we can, f of 0, that's pretty easy. We'd have 0 minus 0 minus 0 minus 4.32. So 0, negative 4.32. The turning points, we'll need to use our graph for those. The domain we should be able to know without our calculator. It's just always negative infinity to infinity, all real numbers for any polynomial. The range also we should know without a calculator because of the end behavior. We know one side is dropping down and the other side is going up without bound, and we know it's connected in between. So the range has to be also all real numbers. Intervals of increase, intervals of decrease will depend on what's going on in the middle here, so we don't know that without looking at the graph. Okay, so let's graph this thing. We have x cubed minus 1.92x squared minus 5.624 x minus 4.32. Okay, and for a window, let's just do our standard window for now and then see what we need. It looks like we need to see a little bit lower, so let's adjust it down, move our y-min down if we want to see lower, right? So let's make it negative 30 and see if that's low enough. Looks like it is. So in this window, we can see the high and low points, and we can see the right end behavior. So that's good. Let's adjust this a little bit. I don't need to see as much to the left and right, so I'm going to change my x-min to negative 5, say, and my y-min, or x-max to 5. Okay, so that looks like a good window to use to analyze this graph. The first thing we wanted to define was our x-intercept, and remember that's where the function is 0, so we want to go to the calc menu and find the 0. And it's asking us for a left bound, just anywhere to the left of that point. And a right bound, it looks like if I do 5, that would be plenty far to the right, so I'm just going to enter 5. And my guess, I don't care. So we've got this for our 0. I'm going to copy that to screen because this is something that can be confusing. So when we did our calculation, what we found was this at the bottom of the screen. When you see something like this, that means negative 1 times 10 to the negative 12. Oops. Which would mean 11 zeros and then a 1 and negative. So anytime you see this a negative number that's larger than 2, you can treat that as 0. The issue is that the calculator isn't able to compute it right to exactly 0. It's just landing slightly short of 0. So you need to know that it means that y is 0. So the x-coordinate there, which is what we're interested in, is 3.74, roughly. So we've got 3.74, 0 we would use. And then the turning points, let's go back to our graph. Now we want this high point here and this low point here. So if I'm looking for that high point, I need to make sure that I'm choosing the option of maximum. So I'll go to that calculate menu and I have to say, okay, I want for the one on the left, that's a maximum. Left bound, I'm going to type in negative 2 because that's somewhere to the left of it. And right bound, I'm going to type in 0 because that's somewhere to the right of it. Guess, I just hit enter and I see this on the bottom of the screen. I'll copy that. So one of the turning points is here at negative 0.87 for the x and 1.54 for the y. And then the other is this low value over here, this relative minimum. So now we'll go through that menu again, and we'll choose minimum instead of maximum. It's going to ask us that left bound, right bound question again. I'm going to put in 1 for a left bound because that's definitely to the left of that point. Hit enter. Right bound, I'm going to choose 3 because I can see that that's to the right of that point. And then guess, just hit enter. And now we get this 2.15, negative 15.35 roughly. So I'll paste that in here. Okay. So now let's put this all together. So the turning points are at negative 0.87, negative 1.54, and at 2.15, negative 15.35. I'm going to copy that graph so that I can write on it. Because now we want to look at the intervals of increase and decrease, which depend on those turning points. Okay, so we found these turning points to be, this one down here was 2.15, negative 15.35, and this one up here is negative 0.87, negative 1.54. So I'm going to highlight on the x-axis the places where the graph is going up first. So intervals of increase, it looks like we're going up, 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 up until we get to that relative max point. Then we're going down for a while. And then once we hit this relative min point at 2.15, we're increasing again. So again, the intervals of increase are always x intervals. We don't care what the y values are, we just care that they're going up over this x interval. Looks like negative infinity to the x coordinate of this high point, which is negative 0.87. And we always list them as open intervals, so we don't include the endpoint. And then the other stretch appears to be this x coordinate of the low point, so 2.15 to infinity. And then the interval of decrease, there's just 1, and I'll highlight that in blue here. That's going to be from the relative max point to the relative min point. So the x interval would be negative 0.87 to 2.15. So we usually are not able to, without a calculator, figure out the high and low points. When you take a calculus class, that's something you'll learn there, how to do that without a calculator using calculus techniques. But at this point, the best we can do is find the x-intercepts, the y-intercept, and then use the multiplicities to get the right behavior, and also to get the end behavior, we look at the leading term and its coefficient. Okay, and then this is just a fact about the number of turning points a polynomial graph can have. So the rule says that a degree n polynomial can have at most n minus 1, so 1 less than the degree, extreme points or turning points as the book calls them. So 1 less than the degree. And it doesn't, a polynomial doesn't need to have that many, but it's only possible to have up to that many turning points. So for example, a degree 5 polynomial can have at most 4 relative maximum and minimum points, so at most 4 turning points, but it could certainly have fewer than 4 as well. So if we want to find a degree 5 polynomial with exactly 4 extreme points, this is a new kind of question for us. We are just trying to come up with a formula for a polynomial and somehow know about its extreme points. What we do know is that the formula for the polynomial is connected to its zeros, right? So we also know that between two zeros, if the graph is a polynomial, it has to somehow turn around between all the zeros. So a degree 5 could have up to 5 zeros. And if there are 5, each would be multiplicity 1, because we would want just one factor with each one. So let's give this as many zeros as possible. Let's say it actually has 5 zeros, and they're all multiplicity 1. Well, then in between each one, the graph is going to have to turn around. Right? So let's say they're at -2 and -1 and 1 and 2 and 3. We can make them up wherever we want them to be. Then we could say p of x is x plus 2 times x plus 1 times x minus 1 times x minus 2 times x minus 3. So we can just pick any 5 x-intercepts. If we know that those the x-intercepts have, if we have 5 of them, then there can be at least only one factor connected to each one, because we want this to be degree 5. And then we know that the graph has to turn around in between each one, so we'll get exactly 4 extreme points like we wanted. And we can know that for this graph, the leading coefficient has to be positive, because the end behavior is like a positive x to the third or x to the fifth rather than a negative. So this would work, right? This particular polynomial would be degree 5, and it would have exactly 4 extreme points. Right? This isn't the only answer. Any 5 x-intercepts would work. We could probably make this work with 4 x-intercepts, I would imagine, if we made one of them maybe multiplicity 2. Let's see how this could work. Let's say we decide to make this particular x-intercept multiplicity 2. Then if we come up to this, we'd have to turn around. We come to the next one, that one, this one. So we have 1, 2, 3, 4 x-intercepts, and we also have 1, 2, 3, 4 extreme points. So we could take this polynomial. Now we've got x plus 1 squared, multiplicity 2 because the graph's turning around there, times x minus 1 times x minus 2 times x minus 3. That would be another option, right? So pick 4 x-intercepts only, make one of them multiplicity 2, and now we'll still have 4 extreme points. One of them happens to be at the x-intercept, and it will be degree 5 because we have 1, 2, 3, 4, 5 factors involving just x. So a couple options, and you could come up with more, but at least we've looked at 2 of them. Find a degree 5 polynomial with no relative extreme points. If we're going to have no relative extreme points, that means we can't have 2 x-intercepts even, because between 2 x-intercepts the graph would have to turn around. So we'd have to be stuck with only 1 x-intercept. So let's say we have x-intercept 0 even. Just for making it a little different, let's make it negative. But that would work, right? P of x equals negative x to the fifth. one single x-intercept at x equals 0, right? So our simple power function is just going to have one x-intercept and it'll have no relative extreme points. So the point is that a degree 5 polynomial doesn't need to have 4 relative extreme points. It could have 0. That's certainly a possibility. But it can have only up to 4. A couple more here of just coming up with a polynomial with this set of given characteristics. So example 11 is asking us to find a polynomial function with specific zeros, 2 multiplicity 3, which means we're going to have a factor that looks like x minus 2 cubed. Negative 1 multiplicity 1, that's going to be then also a factor of x plus 1 with exponent 1. And 5 multiplicity 2, so we want x minus 5 as a factor, and then 2 as its exponent. Passing through the point 1, negative 80. That is going to be something that's not a factor. We'll think about how to deal with that separately. So let's get started with at least the factors that we know. So x minus 2 cubed, x plus 1 to the 1, x minus 5 squared. And then it's asking us to make sure that p of 1 is negative 80. So let's put in what p of 1 so far would be. We'd have 1 minus 2 cubed times 1 plus 1 times 1 minus 5 squared. That is, so far, okay, so negative 1 cubed, so negative 1 times 2 times negative 4 squared is 16. So this is p of 1 at this point is negative 32. But we want it to be negative 80 instead. So we have to figure out how can we adjust this polynomial so that instead of having the point 1, negative 32, we have the point 1, negative 80, but we still want to keep the same zeros. We can't change the zeros. So we could shift the graph, but that would move the zeros, so we can't shift. So we would want to think instead is about a stretch or a compression. And the way we would make that happen would be changing the coefficient in front, right? So a stretch or a compression vertically will help us get the point 1, negative 80 without moving the zeros. So we'll introduce this coefficient a that we can adjust any way we want to. And if this is supposed to be negative 80, then it looks like a should be 80 over 32. Those both have a factor of 4 at least. We could make that 20 over 8. Those both have a factor of 4, so 5 over 2. So the polynomial we want is p of x equals 5 halves times x minus 2 cubed times x plus 1 times x minus 5 squared. And on an exam, I certainly would be happy to have you leave the polynomial in that form. My math lab might ask you to expand it, so let's go through that just for good measure. So this is fine for me. But if we wanted to expand it, x minus 2 cubed, if you expand that, you can use the cubing pattern or you can just FOIL it out by hand. You'd have x cubed minus 4x, let's say minus 2x squared, plus 4x minus 8. And I'm not confident about the sign on that plus 4x. Instead of using the pattern, let's just FOIL it. Oops. Wah. So if I can just do 2 of the factors at a time, I'd have x squared minus 4x plus 4, and I want that times another factor of x minus 2 times x plus 1, and then times x squared minus 10x plus 25. And then if I multiply the first 2 factors and then the other 2, and then I'll have to do that again. Again, this is going to take a long time, and it's not necessary for a test that I give you, or even on your activities, but on my math lab they might ask you for the expanded form, so we should go through at least one of them. So again, now I want to multiply the x squared minus 4x plus 4 times the x minus 2, and I'd have x cubed minus plus 8x squared minus, where did I get that? What am I doing? Okay, x cubed, and then I'm going to do minus 2x squared minus 4x squared plus 8x plus 4x minus 8. And I want that times x cubed minus 10x squared plus 25x minus 10x plus 25 plus another x squared that I missed. Okay, so I'm going to just double check those. X cubed minus 2x squared minus 4x squared plus 8x plus 4x minus 8. That looks okay. X cubed minus 10x squared plus 25x plus x squared minus 10x plus 25. Okay, then I'm going to combine like terms within those factors. I have x cubed minus 6x squared plus 12x minus 8 times x cubed, looks like minus 9x squared plus 15x plus 25. And then we need to multiply those groups together. So I'm going to take everything multiplied by the x cubed first, so I'd have x to the 6th minus 9x to the 5th plus 15x to the 4th plus 25x cubed. Now I'm going to multiply everything by the negative 6x squared, so minus 6x to the 5th plus 54x to the 4th minus 80x cubed, let's see, minus 150x squared. Now multiply everything by 12x. That's what, 102? No, 108. X cubed plus 12 times 15. 180 x squared, and then 8 times 15 120, yep, 120, that's negative x. Then, let's see, the last group, negative 8x cubed plus 72x squared minus 8 times 15, we just had that. 180, why did we have that before though? Oh, I shouldn't have done this. 8 times 15 x. 8 times 15 was 120. That's negative. And then minus 8 times 25, that's negative 200. I had a mistake in there somewhere. Let me figure out where that was. X cubed, that's okay. Negative 9x to the 5th plus 15x to the 4th plus 25x cubed, that was fine. Negative 6x to the 5th plus 54x to the 4th minus 80. Nope, that's going to be 90 instead. (60 plus 30), so 90x cubed. And negative 6 times 25, that's minus 150x squared. Okay. Then, let's see, what do we have? The next line is multiplying everything by 12x, so 12x to the 4th. And then 90 plus 18, that's 108x cubed. 12 times 15 is 180 x squared. And then I wanted 12 times 25 there. That's where I messed it up. So 12 times 25. (12x times 25), that's what, 300? Then minus 8x cubed plus 72x squared minus 120x minus 200. Okay, so those are all the pieces we need, and then we just need to combine like terms and we're done. This is why I tell you that you don't need to expand it for the test or a quiz or an activity. My math lab, fine if you need to go through all this mess, but for me, especially when you've got a time crunch, leaving it in factored form is just fine. So it looks like there's only one x to the 6th term, so we'll leave that. X to the 5ths, we have negative 9 and negative 6, so negative 15. X to the 5th. And then x to the 4th, we have 15 plus 54, so 69 plus 12, 79 plus 2, that's 81. The x cubes, we have 25 minus 90 minus 108. I'm going to grab my calculator. So negative 90 minus 108 plus 25. Any other x cubes in this mix? Looks like minus another 8. So negative 181. Then the x squareds, we have negative 150 plus 180, that's 30, plus 72, that would be 102. And then the x terms, looks like we don't have any in the first line or the second line. 300 minus 120, that would be what, 180? And then a negative 200. And then multiply it all by 5/2. You could do that, but I'll just leave it in this form. Just distribute the 5/2 and you'll be done. My guess is there's a mistake in there somewhere, but at least you have the idea of what you're supposed to do. Multiply all these factors together and then just expand, expand, expand until you've got all the like terms combined. Alright, so the next one we'll just leave in factored form. So let's construct a polynomial that has this given graph. And what we can see from the graphs is that there's a 0 at -3. So we would have an x plus 3 factor. It appears to be multiplicity 1 because the graph crosses straight through that x-intercept. We also have a 0 at x equals 0, which means we have a factor of just x, or x minus 0 if you want to write it that way. Also appears to be multiplicity 1 because the graph's passing straight through. And then it looks like we have a 0 at x equals 2 that is probably at least multiplicity 2. Also notice that the end behavior is like an even degree but negative. Because the ends are going down instead of up. So even degree with a negative lead coefficient, this isn't quite that, right? We'd want to put maybe a -1. And then let's just see if we put in, say, -2, if we're in the right ballpark for the y values. So if we put p of -2 in here, we have -1 times -2 plus 3, that would be 1, times -2 times -2 minus 2, that's -4 squared. So that's +2 times 16. So 32. So it looks like, yeah, that looks about right. So we can take this to be our polynomial. So again, leaving it factored is fine, but just make sure that the x minus 2 factor has an exponent 2, and then the other factors have exponent 1, and that you have a negative leading coefficient. And the last example here, find a degree 7 polynomial with zeros at 3, -2, 0, and 1. So again, this tells us our factors. So we could take p of x equals, we know we need a factor of x minus 3, of x plus 2, of x minus 0, or just x, and of x minus 1. But so far, this is just degree 4 because I only have 4 x factors in the mix. So I need a total of 7 factors, including repeated factors. So I could do this any number of ways. I could do a squared on this one and a cube on that. Then I'd have 1, 2, 3, 4, 5, 6, 7 factors, right? So as long as the total number of factors is 7, but I don't introduce any other factors and I don't shift this up or down, I should satisfy the requirements. So this would be degree 7 and it would have zeros at the right places. All right, so later in this chapter, in a video or two later, we're going to look at how do we find the x-intercepts if what we're looking at is not easy to factor. So we'll increase our ability to factor these polynomials so we'll have tools more than just reverse FOIL or factoring by grouping. So that's soon to come.